Let's talk about sorted array-based collection. Remember from the previous chapters when we deal with fixed size array-based collection, the get, contains, and removes methods requires finding the target, which will cost your application O of 1 in time. However, when we add an element, it is O of 1 because we already know the num element, which means the location of the next available spot inside this collection. Therefore, that approach is fast add, but slow find. This behavior may not solve the business requirement requiring fast retrieval, meaning fast get, fast contain, fast remove. And the examples is when you have a web service that uses the underlying collection, you want fast retrievals on most of the transformers because this web service is getting a lot of requests in real time. In that case, you would want to modify your collection by making the array sorted. In a sorted array approach, we can make use of what we call binary search. Binary search is a very efficient find algorithm that gives you O of log n time, therefore making your get and contains as well as remove O of log n instead of O of n, which is a lot more expensive in time than O of log n. Let's go through some details in the next slides. In our example, we will sort our elements based on their natural order. Therefore, we intend to use the compare to methods associated with the elements. In order to do this, we must ensure that the only classes that implement the comparable interface are used with our collection. So let's look at the following slides with more details. In this sorted array collection, we will enable this collection to enlarge itself by doubling its capacity when a number of elements is filled. So you can think of this collection as a vector, dynamically sizable. To do that, we're artificially invoking its enlarge method by doubling the capacity of the original array and copying everything over. So this is what we call unbounded implementation. In addition, our find methods will use binary search algorithm, which is O of log n, natural log 2, n in time. In order for find to work, we have to ensure that first, these elements are in their natural order, either ascending or descending. When we compare our target against any elements inside this collection, these elements must be cast or implemented with comparable interface. This is where some compilers may generate a warning, but this is not an error. Once your elements are implemented with comparable, you can then use compare to. That allows for the comparisons of the elements based on their natural order. Let's look at add and remove next. Let's look at the add methods. For example, we're inserting BOL into this naturally sorted array. We cannot insert BOL all the way at the end. This would have been fine had the array not been sorted. So the very first thing we need to do is to identify the location of this BOL should be at and insert this BOL into it. Once we insert this BOL into the intended target, then we need to shift all of the existing elements one over to the next available spot. If we don't do that, then you end up overriding the existing value, BRA, with that of BOL, which is unintended. So it's a little bit of work for add because it involves shifting every element one over. And this shifting is O of n because you could end up shifting every single element inside the array, worst case scenario. Also, the find method, remember, is O of log n because we're using binary search. So the efficiency of your add to ensure this property is O of log n plus O of n. This is if we don't have buffer overflow, because in that case, we'll have trigger the dynamic resizing capability, which is the enlarge we talked about. That's another cost. So that completes the discussions on add. Let's look at remove. Remove is the opposite of add in terms of the algorithm. So if you look at this, remove removes the elements BOL from the collection, but because we must preserve the order of the elements, every single element needs to be shifted to the previous spot. So this is O of n operation. Also, the remove calls for O of log n because you do have to search for the location of the target. And notice that in add and remove, we must increment and decrement the elements respectively. We will not be looking at the implementation details. Let's do some comparisons on how efficient this type of approach is when we're dealing with a sorted array. Let's use the vocabulary density example that we illustrated in a different video. and use the two approaches that we talked about. One is the fixed size array collection, and the other one is the sorted array collection. Notice the sorted array collection has the O of log n find, whereas array collection has O of n find. Notice that when we have 1 KB elements, this means 1,000 characters because each byte is 1 character. Execution time it takes for array and sorted array is about the same, very close to each other. And as we increase the number of characters from 1,000 to 177,000, you can kind of see the execution time in comparisons. Of course, when we get into 608 megabytes, so this is 608 million characters. One approach gives you 10 hours and the other one 7.2 minutes. So this tells you something about the efficiency of the algorithms. Also, at the same time, based on this statistics, when your input size is small, it makes very little difference whether you use array collection versus sorted array collection. So you don't need to even bother with binary search if input size is small. However, when you have a large input size, binary search trumps O of n by a huge margin. Hopefully you are able to glean this insight by associating the concepts that we discussed in this video. This completes our discussions on the sorted array-based collection implementation.